So let's make use of the framework that we have come up with over here and build a thermometer. So you guys will get a basic understanding of how one builds a thermometer. The first thing is we need to decide on what is important for us. So I want to measure from 0 degrees Celsius to 100 degrees Celsius. So that is decided, benchmarks basically. Material that we are using gas. So we are using gas, and the property that we are using is, so let me talk about this. So we are building a thermometer. So using gas, wherein the property that we will use is constant volume. When we have constant volume, right, pressure and temperature are related in this way. So this we know from PV is equal to N into R into T, correct? Right, guys? So this is the property that we are using. So the setup is quite simple. Actually, I can draw it, but it will take time. So this is a setup. So let me take it up. Okay, so this is a setup. So from here, let me actually mark it. From this space to this entire thing is your volume. So this part of the tube, or whatever you want to call it as, we have to see to that the gas remains at this level. So that's why we have the 0 marking. And that's how we keep the volume to be constant. So let me explain it this way. So we are looking at this particular scenario wherein we are trying to keep the constant volume. So how is that we are keeping the constant volume? That I'm trying to explain. The point is, if I heat this up, what happens? This is the one which we are measuring. So let me write this. The liquid that we are measuring is this particular thing. Okay. So whatever liquid you are seeing shaded a bit, so that's the liquid we are measuring. You are measuring the temperature of that particular liquid. Now the gas is over here. Right? And the 0 level is over here. That's the 0 level. So when you heat the liquid, what happens? The gas expands. So basically this comes down technically, right? Because the force is more, it pushes. So what we do is we adjust this is flexible. So we adjust, we make it go up and down. This particular column, we make it go up and down so that this becomes 0 again. So that's how we keep the gas volume constant. Again, I repeat, we are trying to keep the volume of the gas constant. How do we do that? When we increase and decrease the temperature, the liquid over here will go up and down. So I'll be able to fix it at a particular 0 level, which we have marked over here, by moving this tube, right? This is flexible. This is actually supposed to be a plastic tube, a rubber basically, not plastic, sorry, rubber tube that will be flexible. So we make this go up and down. And since we can make it go up and down, we can adjust this particular mercury level so that this is exactly over 0, this 0 level. That's our reference point. So how do you find the temperature from this? That I'll be talking about. But point is, you need to understand how the volume is fixed. So we are talking about fixed volume, right? So how is that we are fixing that volume? By adjusting this particular column. So when you adjust this particular column of mercury, this level also changes, and we can see to that every time whenever there is fluctuation over here, every time we can adjust this so that it becomes 0. So that's the basic idea. Okay. So what happens if we adjust this as a 0, and how do we find the temperature out of it? Well, we have to go back to our fluid topic. So we know that the pressure over here and the pressure over here will be the same because they are at the same height. This height will give us the pressure acting upon by the mercury, and since this is open to atmosphere, we can also add the atmospheric pressure. So this will give us this height. From this height, we'll be able to get the total pressure of the system, or the gas actually. Technically, we'll be getting the pressure of the gas. Since the pressure is proportional to temperature, or the temperature is proportional pressure, what we can do is we can draw a graph. Okay, and so on and so forth, depends on the gas and stuff. Anyways, I'll just take one. So now we know the gas, right? Pressure in the gas. So this we know. If I know this, since I have the graph, right? So this is pressure and temperature graph. Say the pressure is at 10 something, 10 unit. Let's not go into the values and everything. Let's take it as 10. So what will I do? Okay, I got 10 over here after calculating. So I'll go to this graph. I will project this point onto the line and then project it down onto this graph, or to this axis actually. So this particular point will be the temperature that this liquid is in. Okay guys, again I'll repeat. So we are looking at measuring the temperature using the fact that pressure is directly proportional to volume for a constant volume. Pressure is directly proportional to temperature for a constant volume. So based on this fact, we are doing this. How do you keep the gas in this case constant, the volume to be constant? By adjusting the column. This is the mercury column, right? I'll make it go up and down and see to that the zero level is fixed. Now, once I have done the zero level, I know the pressure at point A and point B are the same. So I can find the pressure at point B by using the simple fact and using the height, right? You have rho g h. You know the rho value, h value, we can measure it, and g you know. And atmospheric pressure also you will know. Add that up, you'll get the pressure. Once I get the pressure, I'll go to the pressure. Okay, so this is pressure, temperature graph. So I'll find the value on this line, project it onto this, this line. This is your pressure P and T line basically. And from here, I'll project it onto the x-axis. So that's the entire funda. Okay, so let me show you guys the write-up. So we are looking at constant volume gas thermometer. The principle is that at constant volume, the pressure of a gas changes linearly with temperature, right? So how do we calibrate? So next is, once we know all of this, what do we generally do? We make use of all of this property. All of this is fixed. Next is your calibration. So I'm talking about the last step. So since from this formula, we know that it's linearly changing, so we don't have to break our heads. All we have to do is find the maximum and the minimum. So in this case, the minimum is 0 degrees Celsius and the maximum is 100 degrees Celsius. So to measure 0 degrees Celsius, we are taking a mixture of ice water mixture. Why ice water? That we'll understand. Why not just ice? Why not just water? That we'll understand when we talk about latent heat and all of that. Okay, guys. So that's a different topic. So that will come after. I think that's the next topic. Yeah, that's the next topic. Doesn't matter. You'll be studying in the next set of videos. So why ice water? Why not just ice? Why not just water? So that I'll be able to explain better over there. Okay. Now, so we are taking ice water in the flask. Then we will dip the flask. Sorry, we are taking ice water in that container. When I tell container, I'm talking about this. And dip this, what is this called as? Flask. Dip that flask in the ice water mixture. Then we adjust the reservoir so that the 0 mark, column A, this is column A, is at 0 mark. So once we have that, you measure the height, and through that you measure the pressure, and that you take it on to pressure temperature graph. So you have to plot it. Okay, so you will have an empty pressure and temperature graph. So remember, so what we are doing is we have the setup. We dip in ice water. and then what do we do? Dip in ice water. Then you measure the pressure, right? Pressure of the gas will be pressure because of this rho gh of the height, and the atmospheric pressure because we have opened it to atmosphere. Next, so once we know this value, you go to your pressure, temperature. So say I'll take the 0 as, actually this is convenient, but anyways, I'll take the 0 over here. We also have negative now, so let's not talk about that. So we'll just consider 0 over here. Now for the 0, we have a particular pressure, right? So we can call this as P0 degree. So now you take this as your coordinate, right? 0, this is 0 degree, comma, P0 degree. Next, you take the same setup. So in that flask, what you take is hot water. So that technical word is, where is it? It's over here. Flask placed in a steam bath. Again, you adjust the mercury reservoir, make the level in column A to be 0. And now you get a new pressure value, right? So say the pressure is over here on P 100 degrees Celsius. And for that, we know that reflecting temperature is 100 degrees Celsius, and it's over here. So 100 degrees Celsius and P 100 degrees Celsius, right? So I'm just fixing it randomly. Okay. So depending on the graph. And what do I do? Since it's linearly related, I just join this. So this is a setup. Your setup is done. Next, if I want to measure something, what do? I go through the same process. I put the liquid in that particular flask, dip this setup inside this, adjust the mercury reservoir, then measure the height. So with the height, I measure the pressure, and you add the atmospheric pressure as well, and say this is your unknown value, say some random value, Px degree. So I know the pressure. What do? I project it onto the line. And this projection, it's falling over here, and this I project it onto the x-axis. Sorry. Not that. I'm using eraser. This, and that will be your unknown temperature. And that's how you can build a mercury out of gas. Sorry, not what am I telling? That's how you can build a thermometer out of gas, not mercury out of gas. That's how you can build a thermometer out of gas. Sorry, I kind of got distracted from reading on to explaining on the screen. It's convenient, you know. Okay, so all this while I was just trying to explain these few slides. So let me read through properly. So the principle under which we are building this is, at constant volume, the pressure of a gas changes linearly with temperature. So first is we'll figure out the 0 degree marking, right? Flask is placed and adjust the reservoir so that your column A is 0. Height difference H gives pressure at 0 degrees Celsius. Then 100 degrees Celsius is similarly, we will measure 100 degrees Celsius as well. We'll plot it on the PV graph. So to figure out the unknown temperature, put the flask in contact with the unknown temp system. Adjust the reservoir until mercury level is 0. Mercury pressure is figured out, right? Use P versus pressure versus temperature graph to read the temperature. And then, yeah, that's it. That's it. What is the advantage? Very sensitive. Gas expands uniformly and linearly. All gases have nearly the same expansion coefficient at lower pressure. Very wide temperature range. So apparently with helium, we can go down till minus 270 degrees Celsius, and nitrogen up to 1600 degrees Celsius. Disadvantage, not a direct reading, right? We have to do that lengthy process. Bulky setup, clearly. Gas is gas in bulb. So gas in tube, right? You remember, even the entire setup can expand and all of that. So there's a bit of required corrections as well, mathematical corrections. Only then you will be able to. So there is a bit of working. So why is it important? This leads to the definition of something called as absolute temperature scale. Okay, guys. So basically, we are going on to a very important topic, absolute temperature, and we use this. Many TV shows use it. Many people quote this. Many people talk about this in movies and serials and all of that. So it's an important concept, right? So it's quite unique concept. I mean, it's really, if you guys are into science, so you find this interesting. So all of this, set of discussion is leading up to something called as absolute temperature scale. Okay. So yeah, you might feel that I made the video a bit lengthy, but it's okay.